Example 9.5. In a huge oil tanker, salt water has flooded an oil tank to a depth of H2 equals 5.00 meters. On top of the water is a layer of oil, H1 equals 8 meters deep. As in the cross-sectional view of the tank in figure 9.14. The oil has a density of 0.7 grams per centimeter cubed. To get that in kilograms per meter cubed, you can just multiply it by 1,000. And find the pressure at the bottom of the tank. Take 1,025 kilograms per meter cubed as the density of salt water. So to get this, we will take, they want the absolute pressure, find the pressure. Okay, pressure, so it's the absolute pressure they're looking for. So it's going to be air pressure plus delta P1 plus delta P2, which will be, let's see, P sub naught plus rho rho1 GH1 plus rho2 GH2, or P naught plus, we can pull the G out of there and go rho1 H1 plus rho2 H2, if you like, or not. So I'm showing a lot of numbers here that aren't really strictly necessary, but you can see the contribution of about 5 meters of salt water, 5,125, is about the same as 8 meters of oil. And then the contribution of the water and salt water, the combination of salt water and oil is about the same as the contribution of the original air pressure at the surface. In the remarks, they note the weight of the atmosphere results in P sub naught at the surface of the oil layer, then the weight of the oil and the weight of the water combine to create the pressure at the bottom. Seems like they left something out there. The weight of the oil, the weight of the water, and the weight of the atmosphere combine to get the pressure at the bottom. Question 9.5, why does air pressure decrease with increasing altitude? Well, that is because it has less weight of atmosphere above it. Exercise 9.5, calculate the pressure on the top lid of a chest buried under 4 meters of mud with density equal to 1.75 times 10 to the third kilograms per meter cubed at the bottom of a 10-meter deep lake. So this is going to use exactly the same equation. We'll have the atmosphere, 101,300, plus G, and then we'll have 1,000 times 10, plus 1,750 times 4. And the answer comes out to be 267,900 pascals. Example 9.6 asks us to estimate the net force exerted on your eardrum due to water above when you are swimming at the bottom of a pool that is 5 meters deep. Okay, here's me. Okay, I'm looking kind of strange today because I don't have the eyes in the correct place on my head. Let's put them down here. There we go. Okay, scruffy beard, nose, mouth, scruffy hair. Okay. All right, and let's see. There's my eardrum, and we're going to say it's 1 centimeter cubed, sorry, 1 centimeter squared. The behind that eardrum, if I have not been swimming for too long, then it's probably 1 atmosphere on the inside, or 101,300 pascals. And on the outside, it would be 1 atmosphere plus rho GH. So really all I need to find is that rho GH, and we want the force over the area, or wait, we want the force. So we're going to actually take that pressure, rho GH, that will calculate, and multiply it by the area. Force equals rho GH times the area. So rho is that pool, or water. It's probably not a pool. If it's 5 meters deep, that's pretty deep. So the density of water is 1,000. It says estimate, so we don't have to use the correct number for G. We can just change it to 10, and then we'll use 5 for the depth. And the area, well, what is that area? 5 centimeters squared, and we want that in meters. 100 centimeters per meter. We're going to square that. So 5 times 10 to the negative fourth meters squared. And that comes out to be 25 newtons. If we wanted that in pounds, there are 9.8 newtons for 2.2 pounds. Those are the weights of kilograms. The weights of a kilogram comes out to be about 5.6 pounds. You don't want to swim that deep with a quick swim, or maybe you do. Because a force on the eardrum of this magnitude is uncomfortable, swimmers often pop their ears by swallowing or expanding their jaws while underwater, an action that pushes air from the lungs into the middle ear. Using this technique equalizes the pressure on the two sides of the eardrum and relieves the discomfort. Question 9.6. Why do water containers and gas cans often have a second, smaller cap opposite the spout? So here's my gas can, and here's, let's say it's nice and full, so the water level is way up here, and the gas is trying to come out here, but as it does so, the pressure out here stays piece of knot, the volume in here increases, and so the pressure decreases inside there. And so it gets harder to pour it because the pressure inside here is decreasing. But if you add a little hole right there, then the pressure can stay the same inside there, and it will pour. Exercise 9.6 asks us, an airplane takes off at sea level and climbs to a height of 425 meters. Estimate the net outward force on a passenger's eardrum, assuming the density of air is approximately constant at 1.3 kilograms per meter cubed. And I was about to say that once again the area of the eardrum is about 1 times 10 to the negative fourth meters squared. But then I realized that I have just now done a calculations where I set the area of the eardrum to 5 centimeters squared, and over here I said 1 centimeter squared, so this should have been 1 and this should have been 1, and this should have been 5 newtons and about a little over 1 pound, 1.1 pounds. So I apologize for that. So it's not, I was thinking that sounded quite deadly when I was reading 5.6 pounds, but 1.1 pounds, maybe not so much. Anyway, so now we have this, and once again, we are just doing force over area equals density times gravity times height. And so the force on the, we want the net outward force, force equals rho GHA, which is 0.54 newtons. And here we've got a much greater height, but a much, much lower density. Yeah, the height has been changed by a factor of about 100, and the density, it has been changed by a factor of about 1,000. So let's talk about Pascal's principle for a second. It says that a change in pressure applied to an enclosed fluid is transmitted undiminished to every point of the fluid and to the walls of the container. So this is particularly useful in hydraulics. If I push this piston down, while that section has lowered, it has raised this. What's important is the depth of the water above it, and so the change in pressure caused by that will be equal to rho g h, the density times gravity times the height that this has moved, that delta x2 there. And so that change in pressure will happen here at that surface, but it will also happen at this surface and this surface. Everything in the container goes up by that change in pressure. We'll get into what hydraulics are really useful for in the next video, but note essentially that here you have a small force through a long distance, and on this side you have a large force over a small distance, and that's the force multiplying effect of hydraulics. But the work done on both sides is the same. Force times distance equals force times distance.